As we look at rate laws, once again, we are looking for experimental evidence that allows us to define the rate in terms of the concentration of our reactants and how each of those concentrations affects the overall rate, whether it's a square relationship, a cubic relationship, a linear relationship, and all of those things are called reaction order. As we look at reaction rate, we look at an order relative to each reactant, but we can also look at an overall order for reaction rate. One method of figuring out your rate law is called sometimes the differential rate law, or more commonly called the method of initial rates. Once again, this comes from experiment, not by looking at coefficients, subscripts, or anything else as we're examining a reaction. So the way we can do that is we run a reaction over and over, changing the concentration of our reactants and seeing what happens to the rate. That's why it's called the method of initial rates, is we repeat the experiment several times, each time measuring the initial rate. As we do that, we collect different sets of data. Often they're numbered as experiments 1, 2, 3, 4, 5, and 6. The rate is measured in a certain unit, molarity per unit time. Here we have moles per liter hour, or molarity per hour. And then we have our concentrations, and those would be measured in molarities. One thing that's very common is you will see, even if the rates are bigger or smaller than one another, we try to align them using scientific notation so we can see relationships that are very easy to understand and apply. So we're going to analyze this data and see how it would get us a rate law, or see how it would turn into an equation giving us orders. So what we do here in our multiple experimenting is hold different things constant at different times. So if I wanted to find out about chemical A here, everything else has to stay the same. So I would be varying my chemical A concentrations while keeping my concentrations of B and the temperature and all other variables the same. Experiments 1 and 2 are a good example of that, where we see B held constant, we see changing of A, and we can see what the result is. So here, when A is doubled from 1 to 2 molar, and this is important, while B is held constant, and we would describe that as experiments 1 and 2 again, the rate remains constant. So both of those have that exact same 0.005 molarity per hour. That means that even when I change A, it doesn't make the reaction go faster or slower. So A has no impact on the rate, or A is zero order. Once we've established A is zero order, we try to repeat or do some new experiments in which we hold A constant while changing B. And that's what we see right here, experiments 1 and 3. So now A is constant, B goes from 0.2 to 0.4 and is doubled, and we see the 0.5 up to 1. That one is doubling. So now we see the relationship that more B means a faster rate, and specifically doubling B doubles our rate. So that means it is first order relative to B. In terms of an overall order, we can say A zero order, B's first order, 0 plus 1 is 1. So this is a first order reaction overall. And we can also solve for K, both in terms of its value, in terms of its unit, and then ultimately we'll have our rate law expression or equation. So the value of K we can get by recognizing we've made an equation here. The rate, specifically the initial rate, but the rate law is true no matter what. The rate equals K, A to the 0, B to the first. Well, I have data about the rate. I don't know what K is. I can plug in a value for A and for B with the correct exponents. Hopefully we notice that it doesn't matter if we plug in an A or not, because that's going to be whatever we have to the 0th power is 1. But then I've got a number, I divide this over, and I isolate K, and K has some value. K is sometimes a huge number in the hundreds, thousands, or even millions, and sometimes it's a really small decimal. It's unique to the reactants and the scenario, so we don't need to be surprised when it is one of those two extremes. When we're looking for K, we can also think about the unit, and it's very common that you're asked for the value of K with the unit accounting for a point as well. So the unit for K, sometimes teachers like to teach this as if just memorize this equation that allows you to solve for it, but it really just comes down to matching up your units. Our rate was measured in molarity per hour. K did not have a unit that we could think of. That's what we're trying to figure out. Well, this was molarity to the zero, so that one really canceled out. So right here in the first order, we've got a molarity on the right and a molarity on the left, but we don't have a per hour, or we don't have a time unit over here. So what we really try to do after we get the numbers to cancel and simplify is to do the same things with the units. Well, I need an hour on this side, and I need it to be on the bottom so that this works out. Beware that it's very often that it's specific. More often than not, you'll see the unit of seconds, but you need to make sure that you're matching the specific data that you're given, whether it's seconds, minutes, or hours. And then the other thing here is that after we know K, we could also be given new concentrations and solve for a rate. Once we know most of our variables, we could be solving for any of the others. So right here, some of the things that I said about K are important. K, once again, is a constant, but unique to that reaction and unique to that scenario. I've said this before, but to say it here again, when we change temperature, we do get a new value of K because the rate constant is temperature dependent, because the rate is temperature dependent. But then in terms of units here, time is mostly measured in seconds, but it could be measured in minutes, hours, as we just saw. It could even be days. Those are the most common. When we get to really long reactions, maybe a half-life of a nuclear reaction, it could even be in years. Sometimes you'll see molarity written as moles per liter. Sometimes it's just written at the M. I a lot of times will combine it to an M when I see it up here written as moles over liter hours, because I want to just have that as simple as possible. I don't want any more fraction bars. So put those together, keep it simple. Remember, we might run into some other units, but you're really going to see molarity the most. So here I have for 0, first, second, third, and all the way up to fourth order reactions, how the K would work out. I don't want you to try to memorize these, but just to look at them and recognize that in each case, we want our unit on the right to cancel out so that it's molarity over time. Every time the K has a time on the bottom, and it has however many molarities are on the bottom necessary to cancel out all but one of the molarities, because we want one molarity on top and a time on bottom on the left. So we'll practice this with some problems, and then we'll also see that there are other methods to get the rate law using data from experiments.